Consider the Haber process, which is the synthesis of ammonia gas at 700 Kelvin, where 1 mole of gaseous N2 reacts with 3 moles of gaseous H2 to give 2 moles of gaseous NH3. We are given equilibrium concentrations of all three species. Upon writing the Kc expression or formula and substituting these equilibrium concentrations into the formula, we get 0.297. Say we decide to stress the system. We add N2 so that its concentration is now 3.51 molar, higher than before, but we don't make any changes to the concentrations of the other two species. By coming up with a reaction quotient expression QC and substituting these concentrations into QC, we get 0.173. Then we compare this QC value with the Kc value. 0.173 is less than 0.297. Since QC is less than Kc, the equilibrium position shifts to the right. Let's take a closer look at the example graphically. There are 4 stages in the concentration against time graphs of the 3 species shown. At the first stage, a period of time when all 3 species are living in peace and harmony, all 3 graphs are level or horizontal. That is, their concentrations are constant, though not equal to one another. This refers to the system at dynamic equilibrium. Rates of forward and backward reactions are equal. Kc equals 0.297. At the second stage, a point in time, the stress or disturbance is applied. More N2 is suddenly added to the system. The N2 graph shows its concentration jumping abruptly from 2.05 molar to 3.51 molar. Doing this shocks the system out of equilibrium. This corresponds to QC being equal to 0.173. At the third stage, the system is reeling from shock. Instinctively, the upset system feels the need to oppose the change. But what is the change or stress applied? It is an increase in the concentration of N2. What does oppose mean? It means to do the opposite of something. The system fights back by doing the opposite, that is, to decrease the concentration of N2. How does the system get rid of the extra N2 molecules? The system can't eject the extra N2 molecules from the container. But what the system can do to bring down the N2 concentration is by using up the N2 molecules. It makes them react with the H2 molecules present to produce some ammonia molecules. Although the system's wish is to totally rid itself of all the newcomer N2 molecules in this manner, it is unable to get all of the extra N2 molecules to react with H2 molecules. It can only compel a small number of N2 molecules to do so. As that happens, H2 concentration decreases a bit and ammonia concentration increases a bit. The fourth stage of the reaction is where all 3 species achieve equilibrium once more. Their concentrations plateau and no longer change. They are now living in peace and harmony with one another. However, this is a new equilibrium, as the new equilibrium concentration of each species is different from the species' original equilibrium concentration, as can be seen from the graphs. Having said that, the system has returned to achieving its old equilibrium constant Kc of 0.297. Adding a reactant or removing a product causes the equilibrium position to shift to the right. For example, for the Haber process reaction, adding N2 or H2 stresses the system. The change is adding extra reactant molecules. The system feels uncomfortable with the flood of new molecules and opposes the change. It subtracts, so to speak, the extra reactant molecules. Its way of doing so is to use up some of the extra molecules. It makes them react with the other reactant molecules present to give product molecules. The position of equilibrium thus shifts right. Another way to stress the system is to remove the product ammonia. The change is to minus ammonia. The system is unhappy as it misses the ammonia molecules that used to be around. It will think to itself, "Where has my ammonia gone? I need to make more ammonia." so its response is to do the opposite, that is, to add ammonia. How? It does so by calling upon the reactants present to undergo reaction to form more ammonia. The position of equilibrium thus shifts right. Adding a product or removing a reactant will cause the equilibrium position to shift to the left. For example, removing N2 or H2 upsets the system. The system has grown used to having its usual number of N2 or H2 molecules lying around. Once they are gone, the system hatches a plan to recreate them. Since the change is minus N2 or H2, the system's response is to add N2 or H2. It does so by calling upon ammonia to convert some of itself into N2 or H2. The position of equilibrium shifts left. Another way to stress the system is to add ammonia. It isn't happy to be flooded with the extra molecules. What is the change? Plus ammonia. Instead of doing nothing, the system actively responds by doing the opposite, that is, to subtract ammonia. Its way of doing so is to force some of the newcomer ammonia molecules to be consumed to become N2 and H2. The position of equilibrium shifts left. Here is a summary of what we have looked at so far. When a system is disturbed or stressed by the addition of a reactant, some of the extra reactant is consumed along with any other reactant present, if applicable, to form the product or products. This gives rise to an increase in the concentration of each product. When a system is disturbed or stressed by the addition of a product, the extra product is consumed along with any other product, if applicable, to form the reactant or reactants. This leads to an increase in the concentration of each reactant. When a system is disturbed or stressed by the removal of a reactant, some of each product is sacrificed and used up to undergo reaction so as to replace the missing reactant. Another reactant, if applicable, will also be formed in this process. This gives rise to a decrease in the concentration of each product. When a system is disturbed or stressed by the removal of a product, some of each reactant is sacrificed and consumed to undergo reaction so as to replace the missing product. Another product, if applicable, will also be formed in the process. This leads to a decrease in the concentration of each reactant. For all the specified scenarios, the equilibrium constant Kc does not change. The new equilibrium concentrations will be different, but Kc value will still remain the same. Here is an example. Hydrogen sulfide, H2S, is a contaminant commonly found in natural gas. It is removed by reaction with oxygen to produce elemental sulfur, as shown in the equation. For each of the following scenarios, state the equilibrium position for A. Addition of oxygen, B. Removal of H2S, C. Removal of H2O, and D. Addition of S. Strategy. Use Le Chatelier's principle to predict the direction of shift in each case. Remember that the position of the equilibrium is only changed by the addition or removal of a species that appears in the reaction quotient QC expression. Recall that pure solids do not appear in QC. Because sulfur is a solid, it does not appear in the expression. Changes in concentration of any of the above species will cause a change in the equilibrium position. Addition of a reactant or removal of a product that appears in the expression QC will shift the equilibrium position to the right. Removal of a reactant or addition of a product that appears in the expression QC will shift the equilibrium position to the left. A. Addition of oxygen will shift the equilibrium position to the right. B. Removal of H2S will shift the equilibrium position to the left. C. Removal of H2O will shift the equilibrium position to the right. D. Addition of S will not affect the equilibrium position.